Thank you, Jin. It's my pleasure to be here and share my research with you all. I am Shreya Arora. I'm a postdoc at Geological Survey of Japan. For my PhD, I worked extensively along the Himalayan arc. And I consider myself fortunate enough to have worked in Himalaya because Himalaya has inspired a lot of paleoseismologists and world geologists to propose basic concepts of paleoseismology. So from my training from the Himalaya, I'm currently working in central Tohoku region in Yokote Basin. But today, I will discuss with you some of the still unanswered questions regarding the seismic hazard assessment of the Himalaya. One of the main questions that is encircling the Himalayan researcher is it possible for Himalaya to host a mega thrust type event? So before going into detail, let us see what a mega thrust or mega subduction earthquakes are. Mega subduction earthquakes are those which occur along a subduction plate boundary and have a moment magnitude of 9 or more than 9. In the past, in Gutenberg's classification, this mega thrust earthquake was not included, but later on it was added to the magnitude list. Some of the examples of mega subduction earthquakes are 1960 Chile earthquake, 1868 Peru earthquake, 1964 Alaska earthquake, very recent 2011 Tohoku earthquake, and 2004 Andaman earthquake. I think in 1970, huge research began to identify which subduction zone can host a mega subduction earthquake. And I think it was maybe after 1964 Alaska earthquake that people wanted to know which subduction can host a mega subduction earthquake and which subduction zone cannot. So for a subduction plate boundary to host a mega subduction earthquake, they need to fulfill certain criteria. And the criteria are as follows. The subducting lithosphere must be young and light enough to show 100% coupling. When I say 100% coupling, I mean that the subducting plate is stick tightly with the overriding plate so that the strain which is accumulated at the interface is released only during an earthquake. There is no seismic creep. Second, higher convergence rate. When I say higher convergence rate, I mean that faster that strain will be accumulated at the plate interface, and then it will be released during an earthquake. And third criteria is the fault area of mega thrust earthquakes are usually quite very long, around 1,000 kilometers. When I say long, that means the earthquake has ability to rupture a very long plate margin. So if the rupture length is very long, that means the magnitude is also indirectly very large. But 2004 Sumatra Andaman earthquake and 2011 Tohoku earthquake changed that pre-thought process. Initially, it was thought that the segment boundaries can restrict or can arrest the lateral propagation of the earthquake ruptures. But it didn't happen during 2004 Sumatra Andaman earthquake. The earthquake nucleated here, and it ruptured the 420 kilometer of the segment of the plate interface. And then in the next 230 to 350 seconds, it ruptured more 300 kilometer of the length, but it didn't stop there. It went ahead and ruptured more 500 kilometer of the plate interface. So during 2004 Andaman earthquake, almost 1,300 kilometer long plate interface was ruptured. Moreover, the subducting plate is old and dense, and the plate motion of Indian plate is relatively slow. And similar thing happened during the Tohoku earthquake. It was initially thought that this plate margin cannot host a mega subduction earthquake. And it was inferred based on the identified segment boundaries. These segment boundaries were identified based on variable strike and past earthquake seismicity. But in Tohoku earthquake, this whole arc got ruptured. Moreover, the ruptured lithosphere of Tohoku earthquake is over 120 million years. So we can say that the geometrical irregularities along plate interface are unable to control the lateral propagation of the rupture during these two earthquakes. So I think after that, research began to understand whether Himalaya can host such large magnitude earthquakes or not. So for Himalaya to host a mega subduction earthquake, it needs to show strong coupling, higher convergence rate, no along strike segmentation. These three things we can know from geodetic measurements or from gravity data. And fourth is historical paleoseismic record. If we can show that in past that there was a mega subduction earthquake, then the probability of it happening again is still high. And how can we show through paleoseismic studies? If in a trench, we can get a co-seismic, single event slip of maybe more than 10 meters, then we can say that the magnitude must be very large to produce a co-seismic slip of 10 meters. And so Stephen and Evok in 2016, through geodetic measurements, have suggested that there is a strong coupling along the Himalayan arc, and there are no physical or structural asperities that could arrest the lateral propagation of the rupture. Also through paleoseismic studies, it has shown that the historical 1100 AD had the slip of around 13 meters. So the largest earthquake in Himalaya can exceed magnitude 9 at 63% confidence level. However, there are another set of researchers which have shown that Himalaya is segmented. And the study was based on gravity data. And they have shown that Himalaya is segmented into four different segments: Northwest Himalaya, Central Himalaya, Bhutan Himalaya, and Eastern Himalaya. Also, through geodetic measurements and also through geological measurements, it has been shown that the convergence rate of Himalaya is variable. In Eastern Himalaya, it is around 23 millimeter per year. In Central Himalaya, it is around 21 millimeter per year. And in Northwest Himalaya, it is 14 millimeter per year. That means the convergence rate is decreasing from east to west. And the reason for this decrease in convergence rate has been suggested that this Karakoram fault, which is a strike slip fault, could contribute to could absorb some of the slip rate. That is why we are getting lower slip rate in Northwest Himalaya. So for my thesis, I worked in northwest part of the Himalaya, west of this identified segment boundary. So before going into detail of my thesis work, let us first see the tectonic setting of the Himalaya. Himalaya is one of the most seismically convergent plate boundary, where Indian plate is under thrusting beneath the Tibet or Eurasian plate. And this north-south convergence has resulted into several thrust and fold belts. The main fold belts in Himalaya are Higher Himalaya, Lesser Himalaya, and Shivaliks. And these anticlines are separated from each other by thrust belts. We have main central thrust, which separates Higher Himalaya from Lesser Himalaya. Then we have main boundary thrust, which separates Lesser Himalaya from Shivalik. And then we have the southernmost Himalayan frontal thrust that separates Shivalik from the Indo-Gangetic plain. All of these thrusts merge into a subsurface detachment fault, which is known as main Himalayan thrust. This main Himalayan thrust has a typical ramp and flag geometry. It has a frontal ramp, then followed by a flat, and then again mid-crustal ramp, and then again followed by a flat. It has been shown that this part of the MHT is locked, while this part of the MHT is creeping. And it has been suggested that earthquakes which nucleate at the transition of logged and creeping segment of MHT has a potential to rupture whole of this logged segment to produce surface rupture on the Himalayan frontal thrust. I think because of this reason, a lot of paleoseismic trenches have been dug along the Himalayan frontal thrust. However, there are another type of earthquakes in Himalaya, those which can nucleate anywhere on the MHT. And instead of rupturing the Himalayan frontal thrust, they produce surface deformation in the hinterland side, somewhere in the hinterland faults. The example of this kind of earthquake is 1905 earthquake and 2005 Kashmir earthquake. Since in last couple of decades, a tremendous paleoseismic studies have been carried along the Himalayan arc. Almost 30 trenches have been dug till now along 2,500 kilometer Himalayan arc. And the aim of these trenches are to measure vertical slip, past earthquake chronology, number of events, and reoccurrence interval. Vertical slip is important to know because then we can distinguish whether there was a megathrust earthquake or not large magnitude earthquake or a giant earthquake. Similarly, number of events are also very important. Say, for example, in a trench, you get a slip of around 10 meters. Then we need to identify whether it's a single event slip or there were two events in the trench. If it is a single event slip, that means the magnitude must be very high to produce a 10-meter slip. If there are two events, that means the slip is distributed between the two events. And if possible, we can estimate reoccurrence interval. However, despite having so many trenches, there is still some uncertainty to constrain the time and rupture extent of the historical earthquakes. So I decided to highlight how can we overestimate seismic hazard assessment in Himalaya because of the constraint in dating techniques. So what we did, we recalibrated the most recent event ages from the trenches that have been dug along the Himalayan arc, from Hajipur in northwest Himalaya to Harmuti in northeast Himalaya. And when we recalibrated these ages, these ages we took either from capping unit in the trenches, and if the capping unit is not present in the trench, then the youngest faulted unit. So when we recalibrated these ages, we saw that the most recent event can be bracketed between 1250 and 1440. And interestingly, in this, there are two historical earthquakes, 1255 AD and 1344 AD. But both of these earthquakes nucleated somewhere in central Nepal. So is it really possible for is it really possible for earthquake to rupture whole of this central Himalaya and then northwest Himalaya to produce deformation in these trenches? May be possible or may not be possible. So some researchers have suggested that the 1344 AD produced had a very long rupture length and produced deformation till Hajipur. So let us consider one situation. For example, this 1905, 1934, and 1950. These are 20th century Himalayan earthquakes. And these earthquakes occurred within a time frame of 30 to 40 years. 1905, 1934, and 1950. Say we want to date these events 300 years from now, and with the current dating technique, we can say that whole of the Himalaya got ruptured in one giant earthquake. But this was not the real case, because now we know that there are three different earthquakes, one in Northwest Himalaya, one in Central Himalaya, and another in Eastern Himalaya. But because of the limitations in dating technique, which have a resolution of plus minus 30 years, we can overestimate seismic hazard assessment, because in trenches, we are unable to delineate two events which occurred within a time frame of 30 to 40 years. So we suggest that because of the constraint and resolution in dating techniques, we can overestimate seismic hazard assessment. And we propose that instead of Himalaya got ruptured in one or two giant earthquakes, there is a possibility that there were overlapping ruptures, and the magnitude was magnitude was around 7.8 or 8.1. So then we decided to excavate trenches in northwest part of the Himalaya here, west of this identified segment boundary. The name is Pinjor Doon. Pinjor Doon lies between Upper Shivalik and Lower Shivalik. It is a dune where all the sediments from mountains are deposited within a dune valley. And several hinterland faults were identified in this Pinjor Dune, and not much paleoseismic investigation was carried out. So for my thesis, we targeted three faults: Pinjor Garden Fault, Jhajra Fault, and this Khet Parali Taksal Fault. This fault was not identified before my PhD thesis, and during my PhD thesis, we identified this fault. So I will discuss the paleoseismic investigation one by one. So before going to the field, we first need to look out for the geomorphic markers. So we used an which we constructed from 2-meter Cartosat satellite image. And then we, and the base of this anaglyph, we used Cartosat DEM. So from that DEM, we have extracted several elevation profiles. Here you can see a very beautiful step in the topographic profile. And we identified this as a fault scarp, and then we went to the field and saw that there is a step in the field as well. We then wanted to see the lateral continuation of this fault, and then we extracted several more elevation profiles. And also mostly in all the profile, we could see a step in the topographic profile. Then at this site, we used drone data. Here you can very nicely see that there is a topographic scarp. And then we measured the elevation of 20 meters here. And here we measured it as 14 meters. Then at this site, we decided to excavate the trench. And trench looked like this, very typical of alluvial fan debris deposit, where we could not find any finer deposit in the trench, and it was all poorly sorted, unconsolidated pebble and cobble clast. Initially, it was difficult to identify fault, but we were lucky that we were able to do it. So I will show you this part of the I will zoom up at this part of the trench. Here you can see shear imbrications. That is, long axes of the pebble are aligned in the direction of the shear. Another strong evidence was juxtaposition of two different litho units. Here it is very fine gravel unit, and here you can see it is the class size is bigger, and it is it looks like class supported, and here maybe, oh sorry, no, here it looks like matrix supported, and here it looks like class supported. So based on this signatures, we have identified the fault trace. And then this is the upper part of the zoomed upper part of the trench. Here you can also see that the imbrications are coming right up to the surface. So the pebbles are aligned here. So the fault has ruptured till the surface. Here also you can see that. So based on this, we have identified the fault trace. And then based on different lithology, color, clast size and type, texture, we have classified the trench into several litho units. And based on cross-cutting relationship between the fault and unit, we have bracketed the event. For example, this fault F1 has cross-cut this unit D. That means the most recent event on F1 must have occurred after the deposition of unit D. So if we can date this unit D, we can bracket the event. This is what we did. We used OSL age from this unit, and the age range we got was 1280 to 1480. But we could not find any capping unit in this trench. So for the upper bound of the most recent event, we used a monument, construction date of a monument. This monument was built on the scarp of this fault. And this monument had, I mean, it's a masonry structure made from bricks and cement. And this monument shows no earthquake related damage. So we can say that no large magnitude earthquake has occurred after the construction of this monument. So the construction date of this monument becomes the capping unit for our most recent event. So we suggest that the latest seismic event in this region region occurred after 1283, but before 1680. We also calculated co-seismic slip of 4 meters in the trench. Then second, a trench was excavated along this fault. This is the field photograph, and the scarp height is around 2 meters. Again, the trench showed alluvial fan deposit, poorly sorted and unconsolidated. I will show this part of the trench. I will zoom up on this part of the trench. Here also you can see shear fabric very clearly. So based on these shear fabric, we have identified the fault in the trench. And you can see that fault has not deformed this overlying unit. So if we can date this unit, we can bracket the event. So from OSL and AMS ages, we suggest that the most recent event on Chhajara fault occurred between 1223 and 1442. Almost similar age range that we got from Pinjore Garden fault trench. Then third trench we excavated along this fault zone. Like I said, this fault zone we identified during my thesis. So we identified this unit based on aerial photographs and then from field survey. Here you can see a development of a sack pond, and then you can here see channel offset. Oh, this is a strike slip fault. This is not a thrust fault. So, so we went to the field and measured the channel offset. It was around 22 meters. Further, a little bit in the hinterland side, we did extensive RTK survey. And in that survey, we also saw that the 10 years. So, and then we were lucky to spot a very beautiful outcrop which showed signatures of faulting. You know, there are juxtaposition of two different litho units: red sandstone of lower Shivalik with the gray sandstone of middle Shivalik. Moreover, you could see that this part has been uplifted. So this fault shows both strike slip plus dip slip component. So it's an oblique a slip fault. So along the trace, we excavated the trench, and it was a beautiful trench where you can see two different lithology are juxtaposing each other. And we were lucky to have finer deposit in this trench. It seems like, okay, first I will zoom up this part of the trench for you to clearly see the signatures. It seems like that fault has pushed the units from bottom, and it has brought these units on the upper part of the trench. So these bottom units seems to have been pushed and brought to the upper part. And also this, here you can see that there is a vertically bedded gravel unit, which is juxtaposing with a very fine unit. So based on these geomorphic signatures, we have identified the fault trace. And based on cross-cutting relationship between the fault and litho units, we have identified 3 seismic events in this trench. For example, this fault has deformed this unit C, but it has not deformed unit B. So if we can date this unit, then we can bracket the event along this fault zone. However, there is another splay of the fault which has deformed this unit B, but it could not deform the overlying capping unit. So based on this cross-cutting relationship, we have identified at least 3 events in the trench. This is the sketch that we have made. And we suggest that the penultimate event in this along this fault zone is between 1219 to 1451. Similar age range that we got from the other 2 trenches, from Pinjore Garden Fault and from Jhajra Fault. And most recent event is between 1744 and 1957. This is the reconstruction of the sequence of faulting. First, there was a deposition of this unit, and then it got faulted. After that, this unit E was deposited, and then again deposition was happening, and then this unit got deposited. After the deposition of C unit, there was a seismic event, and then after that seismic event, which is our penultimate event, there was a deposition of unit B. And after the deposition of unit B, we have 3rd event which deformed this unit B. And the current situation is this: we have a capping unit which is still not deformed till yet. So this is the this was our study area. So from our study, we suggest that the most recent event on Pinjore Garden Fault occurred between 1200 AD, but before 1600 AD. Along Jhajra Fault, we suggest that most recent event occurred between 1200 AD and 1400 AD. And along Khetparali Taksal Fault, the penultimate event is between 1200 AD and 1400 AD. Almost similar age range. And we have 3 historical earthquakes which can be fit in this age range. One, we have 1555. This earthquake occurred in Kashmir, Himalaya. Then we have 1505. This occurred in Central Himalaya. And then we have 1344. This occurred in Nepal, Himalaya. So it is possible that the deformation that we are seeing in these trenches is due to 1344 AD, or is 1555. So in historical records, we do not have any written records of deformation in Northwest Himalaya during 1344. So we can somehow rule this out. Then we are left with these two historical earthquakes, 1555 and 1505. And then both of these earthquakes occurred within a time frame of 40 years. So with the current paleoseismic investigation, it is very hard to say which earthquake ruptured in this area, 1555 or 1505. Also, we compiled paleoseismic data that have been paleoseismic trenches that have been excavated along the Himalayan arc, and we suggest that there is a westward migration of earthquake in historical times. You can see that there was 1100 AD earthquake, and then there was 1250-500 AD earthquake, and then after that there was a sequence of 1505 or 1555 earthquake which ruptured the Western Himalaya. So there is a westward migration of earthquakes. Also, we can see that there is a seismic quiescence in this area during 1400 AD, and then after 1400 AD, we directly have 20th century earthquakes which ruptured the Himalayan frontal thrust. There are evidence that 1950 ruptured the frontal thrust, and also 1934 also ruptured the Himalayan frontal thrust. But no earthquake has ruptured the Himalayan frontal thrust in Northwest Himalaya after 14th century earthquake. So there is a seismic quiescence in northwest part of Himalaya after 14th century. Oh, sorry, after 16th century. So we suggest that there is a clear migration from east to west, that is, events of 1100 AD occurred during 12th century in eastern part, followed by 13th and 14th century ruptures, which occurred in central Himalaya. And we can also see that 1100 and 1200 AD earthquake have extended along this identified segment boundaries, while others were well constrained within these segmented boundaries. So there is a possibility that these two earthquakes were mega subduction, but still, I think more trenches are required to say that. Then we went ahead and thought to date some of the terraces to know the slip rate of this part of the Himalaya, because this part is very crucial, as this area is west of the identified segment boundary. So until now, till now, we have some slip rate data from trenches, but then we thought to date fluvial terraces and determine the slip rate and maybe possible slip deficit. So terraces were already identified by Nakata and Malik. So we extracted the along fault topographic profile, and here you can see that there are beautifully preserved terraces. Then we also extracted fault perpendicular profiles to see that these terraces are tectonically driven, not by climate driven. Here also we can see that the scarp height is around the highest scarp height is around 44 meters, and then the scarp height is decreasing along the subsequent terraces. And then we dated these terraces and calculated the incision rate. Incision rate were almost consistent along all of these terraces. Then we went inside the dune area and targeted Pinjore Garden Fault. So previously we targeted Himalayan frontal thrust, and now we are targeting the hinterland Pinjore Garden Fault. Similarly, we did across fault and parallel fault topographic profiles. And then here you can, this is a field photograph of the terraces, and then we determine the incision rate along the terraces. Here also, we saw that the incision rate was consistent in the terraces. Then using the Lovey and Evoque empirical relationship, we calculated the slip rate, and we estimated that at this area, the convergence rate is around 6.2 millimeter per year. And in Kashmir, Himalaya, it was already calculated by Gavilot, and in this region also, it was already known. So we suggest that the long rate of Kashmir, Himalaya to Dune around 6 to 15.2 millimeter per year. And then we have estimated a slip deficit of around 5.8 meter in this 300 kilometer long Himalayan segment. So I summarize my work by saying that based on compilation and recalibration of radiocarbon ages from the trenches, we have highlighted that there is because of limitation in dating method, we may be overestimating seismic hazard in the Himalaya. Then from the trenches that we excavated, we suggest that along Pinjore Garden Fault and Jhajra Fault, the most recent event occurred after 1200 AD, but before 1600 AD. And along Khet Parali Taksal Fault, we identified 3 seismic events. And the penultimate event is between 1200 AD and 1400 AD, and most recent event between 17 and 1900 AD. The convergence rate of the convergence rate along Pinjore Garden, the convergence rate along Pinjore Dune is around 6.2 millimeter per year. And the total convergence rate between in Northwest Himalaya from Kashmir Himalaya to Kangra reentrant to Pinjore Dune is around 6 to 15 millimeter per year, which is consistent with the geodetic convergence rate of around 10 to 14 millimeter that has been calculated in this northwest part of the Himalaya. So thank you very much for listening to my work that I have done in the Himalaya.
All right, thank you very much.